Assalamu alaikum wa rahmatullahi wa barakatuh, and welcome to the Voice of the Cape Matric Revision Programme. Today, our subject is chemistry with Muntasir Kadri from Intune Tutoring. And today, the subject that you'll be covering, Muntasir?
I'll be covering chemistry. Paper 2 will be specifically looking at chemical equilibrium, which is in every question 6 of every paper 2.
Yeah, so I will hand over to you. Without further ado, we will commence with the lesson. Bismillah.
Okay, shukran. Okay. Assalamu alaikum, everybody. So today as mentioned, we're looking at chemistry and specifically chemical equilibrium, which I find a lot of students struggle with, especially with the ICE table, or some of you might know it as the RICE table. And we'll take a look at that, and we'll be looking at reversible reactions, Le Chatelier's principle, endothermic and exothermic reactions, and hopefully everyone will have a better understanding of this specific topic. Now, if we look at the first question, it states here the dissociation of iodine molecules to iodine atoms is a reversible reaction taking place in a sealed container at 727 degrees Celsius. The balanced equation for this reaction is your iodine molecules over there, diatomic, so it's shown as I2, right? You see it over here. And this symbol here indicates a reversible reaction. When a reaction in equilibrium, you can see that the forward reaction and the size of the forward reactions arrow and the size of the reverse reactions arrow are the same size, so we know it's in equilibrium. And that's going to give us two molecules of two atoms of iodine gas. So they then tell us that the Kc for the reaction at 727 degrees Celsius, or your equilibrium constant, is 3.76 times 10 to the minus 3. The first question is write down the meaning of the term reversible reaction. Well, this is pretty self-explanatory. We can just say that it is basically the forward reaction and the reverse reaction taking place simultaneously, right? And that's basically all it means. There's various definitions in the memo. We can just quickly look at them, but that's one of them. It says here products can be converted back to reactants. You'll get that right. Both forward and reverse reactions can take place. That is correct. A reaction in which a reaction which can take place in both directions. Right? Now, very simple. It's just a definition. So 6.2, at equilibrium, the pressure of the system is increased by decreasing the volume of the container at constant temperature. How will each of the following be affected? Choose from increases, decreases, or remains the same. So they state the value of the equilibrium constant. So, according to Le Chatelier's principle, right, the things that are going to affect whether you produce more products or more reactants are things like pressure, the number of molecules within the container, the volume of the container, and the temperature at which the reaction is taking place. Now, they have mentioned to us a few things. They've told us that temperature, I'll just use a different color over here. And let me just zoom in. Maybe you might not be seeing clearly. Just do this. Okay, there we go. And they have mentioned to us that temperature is constant. Right? So when they tell you that temperature is constant, it is of no concern within Le Chatelier's principle unless they are adjusting the temperature. They mentioned to us that the pressure is increased and the volume is decreased. Now, it's important to note that pressure is actually inversely proportional to volume. Pressure is inversely proportional to volume. And I know a lot of matrics haven't learned this equation, but an equation that helps me understand Le Chatelier's principle quite easily, I'll just go to the whiteboard here, is an equation known as PV equals NRT. And we can see that from this equation, pressure and volume would be inversely proportional, because if we rearrange this equation, we'll find that pressure is equal to nRT over V. So therefore, we can see that pressure is inversely proportional to volume, We can also say that pressure is directly proportional to temperature. And we can say that pressure is also directly proportional to the number of moles, so the number of molecules within the system. And we can do the same thing for volume as well. Right? If we had to rearrange this equation so that volume is the subject of the formula, we'll have V equals nRT over P, and we find volume is inversely proportional to pressure. It's directly proportional to the number of molecules and directly proportional to the temperature. Okay, so that's just a little side note. Now, knowing that, the value of the equilibrium constant, does it increase, decrease, or remain the same? Well, all these factors do not affect the equilibrium constant. As we know, equilibrium constant is equal to the concentration of the products while it's in the gaseous phase over the concentration of the reactants to the power of the, and of course here we're using, we are looking at the balanced equation and we'll be using the number of molecules there in the exponential. So the only things that affect your equilibrium constant, and you can tell from this equation, is number one, the concentration of your products and your reactants and the number of molecules. Okay, so these types of information will affect your equilibrium constant. So increasing pressure and decreasing volume is not going to affect it, so this remains constant. So stays the same, right? Now, the number of I2 molecules. Okay, so this is very important. So if we look at this reaction, we can see that, give me a second, scroll up. They state here, if we read the question, the dissociation of iodine molecules to iodine atoms is a reversible reaction taking place in a sealed container at 727. Okay, at equilibrium, the pressure of the system is increased by decreasing the volume of the container at constant pressure. Now we need to think of what's happening here, right? So what essentially is happening here is they're telling us they're increasing the pressure of the system, right? So we have some sealed container. And in the container, we have, and I'll use different colors for this. Let's say we have iodine. So we can see the ratio is 1:2, right? For every one molecule of iodine, there are 2 atoms of iodine. So this is my iodine in the red, right? So 1, 2, 3, 4, 5, 6. Let's say we have 6 iodine molecules. And here we have, now I'm going to do, iodine atoms. And here we're going to have 1, 2, and this is I2, right? There we go. So we're going to have half the number of I2 molecules compared to iodine atoms in the same container. This is what it's going to look like. How will each of the following be affected, right? So we're increasing pressure. So if we're increasing pressure, what we're going to do is we're actually going to end up squeezing the iodine atoms together. And that's most likely going to favor the reverse reaction, and we're going to get an increase in the formation of the number of iodine molecules. Now let's double check the memo. We can go here, right? And there we go. We have an increase, right? And yeah, that's basically what happens. And well, to clear it up for you. So what essentially is happening is as we're increasing the pressure, these atoms are getting closer to each other, right? So the iodines are basically being squashed together, right? And as they're getting squashed together, a reaction occurs. And we end up with our I2 molecules, right? But of course, as we give them more space and space to breathe, we'll have the effect where the iodine molecules are split up into the atoms under these specific conditions. Now, let's take a look at the next 6.3. Explain the answer to question 6.2.2 by referring to Le Chatelier's principle. Well, all we need to do, once again, we look at this information here. We look at the number of molecules and we look at the ratio. This is 1:2. Right, so we can see that while we heat this at this temperature, we dissociate this molecule. Okay, and we're going to produce more of this over here. But as we increase the pressure, we're going to squeeze these atoms together to form these molecules. Now, what do they say in the memo with regards to Le Chatelier's principle? They say, when the pressure is increased, the reaction that leads to the smaller amount of gas or side with less molecules or number of moles is favored. And they say the reverse reaction is favored. Okay? So that is essentially what we were speaking about when we drew those molecules and we spoke about squeezing these atoms together. Yes, it's going to favor the side that has the lower number of molecules. You could see the ratio is 1:2. Okay, so obviously if you're increasing the pressure, you don't want to make more molecules. You want to resist the production of making more molecules because you want to decrease that increase in pressure. Otherwise, your container is going to explode. Basically, that's what's going to happen. Now, if we go down to 6.4, let's say at 227 degrees Celsius, the Kc value for this reaction is above 5.6 times 10 to the minus 12. Okay, so we can see that this equilibrium constant is much smaller than this equilibrium constant. Is the forward reaction endothermic or exothermic? Well, let's think about this. Okay. If our Kc is decreasing, and we know that our Kc is equal to the change in products over the change in reactants, right? And specifically in this case, we know it's iodine over I2, so we'll actually put that in. So we've got I to the power of 2 over I2. Right. Products and reactants. So let's think about this. So if we want to decrease our Kc, if we want to make it 5.6 times 10 to the minus 12, we need to form more of this iodine over here. Right? We're going to need to make more of these because obviously we want to have a small number divided by a big number to get this value, which is really tiny. Look, it's times 10 to the minus 12. That is a pico. And here we have 3.76 times 10 to the minus 3. Right? Which is basically a, if I remember correctly, times 10 to the minus 6 is micro. This is about a milli. Right? So, as we know, if we want to get it this size, the numerator or the products need to be smaller than that of the reactants. But in the case of this value here, the products needs to be even smaller. So there needs to be even less products as opposed to reactants. And so what is that telling us? That's telling us that at 227 degrees Celsius, we are producing less products. Which means if we're producing less products, we are producing more reactants. So the reverse reaction is being favored. Okay, so think about that. We're decreasing the temperature from 727 to 227, and the reverse reaction is being favored. Okay, that tells us that the forward reaction, so we now know that by decreasing the temperature, the reverse reaction is being favored. Right? That means that this is exothermic. The reason I say that is because in an exothermic reaction, energy is being released. We can think of energy as a product, right? You can also think of it in that terms. So if I go here, we can take a look at this. Or heat. Heat is a product, right? So here we have our iodine reacting to give our I atoms, right? And we find that this side over here, the reverse reaction, actually releases heat, right? So what? So if you think about it, right? If we must add heat to this to cause the dissociation, that means that the forward reaction is endothermic, right? Because if you think about it, an endothermic reaction, it takes heat from the environment, right? And you'll notice that the environment surrounding the container will get cold. If you've ever done an endothermic reaction, you'll feel the container get cold. Okay, and let's say, now remember, you're adding heat because the container is getting cold, right? So you add more heat because it needs more heat. So then we're going to favor the forward reaction. However, if we want to favor the reverse reaction, what do we have to do? If the forward's endothermic, the reverse has to be exothermic. And in an exothermic reaction, energy is being released in the form of heat. So what do we need to do now? Well, we need to remove that heat. That heat is behaving as a product in the reverse reaction. And that will assist us in then favoring the reverse reaction. Right? Because of all the heat being produced, you need to remove it. Otherwise, it's going to get too hot. If you've ever seen a violent exothermic reaction, it's not the prettiest thing. And that is why we actually remove heat from exothermic reactions. Not only to produce more of the products that we want to produce, but also to ensure a safe temperature that we're working at. So let's take a look at our memo. Here we go. So 6.4. Am I on the right one? Yes, I am. Okay, so they say endothermic. Kc decreases with a decrease in temperature. Reverse reaction is favored. Like I mentioned, the reverse reaction is favored. Concentration of reactants increases. Concentration of product yield decreases. Decrease in temperature. Decrease in temperature favors an exothermic reaction, which is what I mentioned. Okay, so this year, I don't know why they're saying endothermic. It's supposed to say exothermic. And they're even telling you decrease in temperature favors an exothermic reaction. So, yeah, I'm not too sure why they're saying, oh, hold on. Did I read something incorrectly? Let me just double check. Is the forward reaction in, yes, that's correct. So the forward reaction is endothermic and the reverse reaction is exothermic, as we indicated here. So we are right. Excellent. Now, 6.5. A certain mass of iodine molecules, I2, is sealed in a 12,3 decimeter cube flask at a temperature of 727 degrees Celsius. Right? And then our equilibrium constant is 3.76 times 10 to the minus 3. They say when equilibrium is reached, the concentration of the iodine atoms is found to be 4.79 times 10 to the minus 3 moles per decimeter cubed. Calculate the initial mass of iodine molecules in the flask. Okay, so let's go ahead and do this. So this is a 9-mark question. This is, of course, where a lot of students struggle, is with the ice table. So we'll add this to a new page here, and we will take a quick look at this. Now, let's gather our information and do a bit of investigation. We know of course, the most important part here is our reaction. So we know that it's I2 reacts to give us 2I. Okay. We know that our Kc is equal to 3,76 times 10 to the minus 3. we know that Kc is essentially equal to our concentration of our products over our concentration of our reactants. Okay. They tell us when equilibrium is reached, the concentration of the iodine atoms is found to be, okay, so we can put this here, concentration of iodine atoms is found to be 4,79 times 10 to the minus 3 mole per dm cubed. Calculate the initial mass of the iodine molecules in the flask. So we have this is at equilibrium. Right? So remember this is at E. Now we can actually therefore calculate the amount of iodine that's going to be at equilibrium. Okay, let's go ahead and do that. And we can use this equation. So we substitute this value in here. Right, okay, well, I'll just do it separately. So I'm just going to make this the subject of the formula. So we can just go, well, I2, concentration of iodine to the power of 2 is equal to, and I'll just write out the formula, is equal to Kc times by the concentration of the iodine molecules. Now this is going to equal 3.76 times 10 to the minus 3 times by the concentration of the iodine, which is 4.79 times 10 to the minus 3. Yeah, where's my calculator? Let's take a look at this. 3.76 times 10 to the minus 3 times by 4.79 times 10 to the minus 3. Oh, I don't think that's correct. Give me a second. And that gives us a value where it tells us that I squared is equal to 1,80 times 10 to the minus 5. Now, we can find the concentration of iodine at equilibrium by just popping in a square root. So we square this and we square this. Right. So that goes away, and then we'll end up with Hold on. Did I do it? Did I do the right thing here? My apologies. When equilibrium is reached, the concentration of iodine. You see, I made a mistake. Good thing I double checked. Sorry. The concept they say here. So it's very important to read the questions carefully. The concentration of iodine atoms. I used iodine molecules. Oops. Second, we'll sort this out. There we go. Concentration of iodine atoms is 4.7 at equilibrium. So this actually makes things a little easier for us as well. So then we can just go, okay, we can find the concentration of the iodine molecules. I2 is just going to equal 4.79 times 10 to the minus 3 to the power of 2 divided by 3,76. It's 10 to the minus 3. Right? And this is going to equal, because this is at equilibrium, let's use this, times 10 to the minus 3 to the power of 2 over 3.76 times 10 to the minus 3. And that gives me a value of 6,10 times 10 to the minus 3 moles per decimeter cubed, right? And this is also at equilibrium. So what do we have? Now we have a concentration of iodine atoms at equilibrium, and we have the concentration of iodine molecules at equilibrium. So how does this help us? Well, this will assist us in finding our initial masses. Okay, now all we need to do is this. So we go to our board, open a new page, and I'll just make a table. Here we go. Here we go. And you know what table we're doing? That's right, the ice table. Right, and this is going to be our reaction. This is our initial. This is our change and our equilibrium. Right. So here I'll just go here, put in the reaction. So this is, let's use a different color. This is I2 reacts to give 2I. This is our initial, change, and equilibrium. Right. Just do this. Okay. Now, we've calculated what we have at equilibrium. But let's think about this. The products that we have initially is none. It's always 0. Right? At equilibrium, we discovered that, our concentration of iodine was 4.79 times 10 to the minus 3. Now, be very careful here, because when we're working with this table, our values must be in moles, right? But when you're calculating for Kc, you have to convert those values to concentration. Now, they did give us a piece of information that will allow us to convert these values into moles, and that is the fact that we are working in a 12.3 decimeter cubed flask. And we know that the equation for concentration is C is equal to N over V. So we just need to rearrange the equation and say N is equal to C times V. And we do it for each of these. So we just take this value and we times it by 12,3. Right? So we're going to find that the number of moles of iodine is equal to 4.79 times 10 to the minus, times 10, again, 10 to the minus 3 times by 12,3. And that gives me a value of 0.06 mole, rounding up. The number of moles of iodine molecules, and we do the same thing, we just say 6.10 times 10 to the minus 3, and we times up at 12,3, and that gives me a value of 0.08 mole. Okay, so 12.3, 3.76, 4.79, yeah, two significant figures is correct. Now we go here and we input our information. So what do we have? We have 0.06 mole of iodine. And we have 0.08 of iodine molecules. Okay. Now, the change part is what often throws students off. Okay. We can see here that the change is plus 0.06 mole. Now, I'll show you a little trick. Normally, you're supposed to, I know in the textbooks they show you to use algebraic manipulation to assist in solving this, but there's a simple tool that you can use, and that's called molar ratios. If we look here, the ratio is 1:2. And you use that ratio to assist you in figuring out what the change is over here. Well, if the change here for the ratio of 2 is 0.06, then the change here has to be half of this because it's half of 2, 1:2, right? So this change here is going to be minus, because we're losing reactants, 0.03 mole. And that means that, of course, our initial value is 0.03 more than that. So it's supposed to be 0.10 mole. Sorry, 0.011. My apologies. 0.11 mole. Now, the question asks us calculate the initial mass of the iodine molecules. Well, now we have the number of moles, so it should be fairly simple to calculate the mass. But let me just consolidate something so you can completely understand what I did here with the ratios, which is this. I'll show you over here. We said 1:2. We don't know the change value here, so we can just say X. And the one that we do know, which is 0.06 mole. And all we do is this, cross multiply. We end up with 0.06 equals 2x. We find that then the value of x is just 0.06 divided by 2, which gives us 0.03. And see, it matches, right? So that's just the thinking behind it. Very, very simple, very easy. It's not too complicated at all. You just look at the molar ratios. That's how easy it is, okay? Now we need to go ahead and calculate the mass. So we got 0.11 mole. No problem. Open a new page. So here we have discovered that the number of moles of the iodine 2 gas was 0.11 mole initially. We know that N is equal to M over M, or mass over molar mass. Manipulate the equation, and we make it so that mass is equal to the number of moles times the molar mass. Now, what is the molar mass for iodine? Well, we just go to our periodic table. Right. And let's see. The molar mass for iodine, so we know iodine's on the right-hand side of the periodic table. And let me just pull up the molar mass. Is 126.9 grams per mole. Okay, so we can just call it, I'll leave it as 126.9. So we go here, and we know our molar mass is 126.9 grams per mole. So therefore, the mass of the iodine molecule, just 2 of those. Now remember, we have 2 of those, so it's 126.9 times 2 is going to give us a value of 253.8. So now we know we got 253.8. So now we can go 0.11 mole times by 253.8 grams per mole is going to equal So we initially start with 27.918 grams. That seems reasonable. Now let's take a look and see if our calculations are correct. Let's go to the memo. And there we go. Between 26 and 27.94. And what did we have? 27.91. So we were on point. Okay. And it's as simple as that. It's really not that complicated. I suppose what might be complicated is working backwards, because of course, if you're used to them asking you just to calculate Kc, which is pretty straightforward, you just need to calculate Kc. They give you concentrations and all of that. But what we're doing here is we're working backwards. So you need to be a bit intuitive with your calculations. It can be tricky because we see this information here, but we can see once they give us Kc, well, we just write down the formula for Kc, and we'll be like, so what do we do here? What values do they give us? Well, they give us concentration. Oh, just There we go. Put the concentration in. Well, then we can then calculate the concentration of whatever variable is not given, right? And we know we're working backwards. So look what we did. We worked backwards. I'll show you over here. We literally worked backwards from Kc to finding concentration. From concentration, we converted to moles. And this is where we use the ice table. And from moles, we were able to convert to grams. See that? Very, very easy. And that was just the steps we took. Normally, the steps you take is the reverse of this. You'd go grams to moles, you'd use the ice table, then you'd go to calculate your concentration, and then you'd get your Kc from your concentration. So you can see how it's just a reverse process, kind of like a reversible reaction. That was just a little chemistry joke there, right? But that's essentially what is going on here, right? So there we go. I hope this lesson was helpful. Okay, I hope it cleared up a few doubts. And when it comes to the ice table, this is a very neat trick which I learned in university. Once I figured this out, I was overusing algebraic manipulation for trying to solve the change in the number of moles. Okay, all I did was go straight to ratios. Made my life a lot easier. You can go ahead and try it yourself with whatever examples that you may have, and I promise you it will work. So yeah, there we go. I hope this was helpful. I hope you understand Le Chatelier's principle a little bit better, and ice tables, and you understand the concepts of equilibrium. And that will be it from me for the rest of the day, and I will see you again next week. Assalamu alaikum rahmatullahi wa barakatuh.
Wa alaikum salam wa rahmatullahi wa barakatuh to you, Muntasir. Shukran once again, and we look forward to having you back next week, inshallah. From myself and the guests this afternoon, we bid you farewell. Assalamu alaikum wa rahmatullahi wa barakatuh.